All right, good morning. This is Math 1314. It's April the 11th. I want a couple of announcements to point out to you. First of all, office hours. Let me remind you again. Sundays and Tuesdays, 8:30 to 9:30 at night, online. Oh yeah, and then also, and I forgot to write this the other day also, but Tuesday, Wednesday, Thursday from 11 to noon. You don't need to make an appointment. I'm here during those hours, so for all of you who are watching this recorded later, don't hesitate to stop by my WebEx room and ask me some questions during those hours. I'd be happy to help you out. Also, I'll be on campus next week, April 18th and 19th. That's Wednesday and Thursday. On Wednesday from 4 to 6 in the afternoon, and on Thursday from 9:30 to 11:30 in the morning. So don't hesitate to stop by my office. I'll be happy to help you out if you come by. So please do that as you're preparing for Exam 3. The Exam 3 review is posted. I posted that, I believe, on Monday of this week. It's a very lengthy review, lots of problems on it, lots of practice problems. It's a very good review for this exam, so be working on that review. Don't hesitate to stop by my WebEx office or my on-campus office if you have questions. Also, the window for Exam 3 opens April the 19th. Last thing here, and this seemed to be an issue on Exam 2, so make sure you understand that it is your responsibility on an exam to get to the center with enough time to take the exam. So whatever center you're at in the Lone Star system that you've decided to take the test, make sure you get there with plenty of time to take the test. They are not going to give you the test if you get there within an hour of them closing. So make sure you know the hours of the center that you're using. And let me emphasize again that this is your responsibility to do that as a student. So kind of pay attention to that. Also, calculators. Make sure that most centers in the Lone Star system, but not all centers have graphing calculators available for you. So if the center you're using doesn't have a graphing calculator available, then you need to have one with you with the memory cleared. Again, that's your responsibility to deal with those kinds of things on the exam. So please, if you have any questions about an exam, I'm in a situation where if you email me 3 days after the window and say, hey, I couldn't take the test because, then it's very difficult for me to work that out. So you need to get in touch with me immediately if there is an issue about something as you're going in to take an Exam 3. Again, these things are your responsibility as a student, so make sure you take care of those going into Exam 3. Today, we're continuing on solving equations. We've been talking about logarithms, and so last time we started talking about exponential equations. We did exponential equations part 1, and so today we've got exponential equations part 2, where you have to use logarithms to solve the equation. And then we're going to move on and talk about solving what I call type 1 log equations that are in the form log of something equals a constant. And then obviously, because I'm talking about type 1 log equations, then I also refer to something called type 2 log equations, and we'll deal with those next Monday as far as getting ready for Exam 3. All right, and if it's even possible, we can talk a little bit about the type 2 today, if we can, if there's, depending on the time on this and everything. If we do, that would be great, because the more we can get done now, the sooner you can get that material as you're getting ready for Exam 3, because this material is all on Exam 3. So, all right. So let's get started with this. All right. So if you remember with exponential equations, we did the first part of that on Monday of this week in my last lecture. And so part 1, which we did last time, involved properties of exponents. No logarithms were involved. These equations could be solved using properties of exponents. So let me look at another problem like that to kind of remind you of what we did with these kinds of equations. So if you had an equation like this, 27 times 3 to the 5x plus 1 equals 9 to the x, let's say, something like that. This was an equation where all the bases are powers of 3, right? 27, 3, and 9 are all bases are powers of 3. And because that's true here, we will not need logarithms to solve this equation. We can use this property instead, that when you have b to the x equals b to the y, right, if the bases are the same, then it has to be true that the exponents are the same also, right? So if you have an equation where an exponential expression equals an exponential expression and the bases are the same in both of those exponential expressions, then it's got to be true that the exponents are the same also. So you don't need logarithms to solve this type of equation. So on our problem right here, 27 is 3 to the third power. So you write it that way. You write everything as a power of 3. Every base is a power of 3. And 9 is 3 squared. So you write that as 3 squared raised to the x. And then on the left side of the equation, I add exponents, right? Because you're multiplying bases, and so you're going to add exponents on that side of the equation. And on the right side of the equation, you are going to multiply exponents, right? You need to know the basic properties of exponents in order to use this method. All right, so on the left side, you have 3. The exponents are 3 and 5x plus 1, so you add 3 and 5x plus 1, right? On the left side, you're just adding the exponents there, because that's the rule of exponents there. And so that gives you 3 to the 5x plus 4 on the left side of the equation. On the right side of the equation, you multiply the exponents, so that's 3 to the 2x, like that. And then finally, what happens here, the only way that can be true, the bases are the same, is that the exponents have got to be equal. So you set the exponents equal to each other, you get 5x plus 4 equals 2x. And then go ahead and solve this for x. So let's see, if I subtract 2x from both sides and subtract 4, to kind of move terms around, right, you get 3x equals negative 4, or x equals negative 4/3. And that would be our solution to this equation, negative 4/3. This would be a typical kind of problem for the exam. This might be on the harder side of a problem like this, but this would be a kind of problem that I would ask on the exam, where you're trying to write the equation so that both sides have the same base, like that. All right, so now that's the kind of problem we did last time. So now in part 2, this type of solution, rules of exponents don't work. Rules of exponents won't help to solve the equation. And so we're going to have to use logarithms to solve this type of equation. So you could start off with something super simple like this. It doesn't have to be a complicated equation in order for rules of exponents to fail you. And so like this problem right here, 2 to the x equals 5, is a typical example of a problem where I can't raise both sides. Both sides are not powers of the same number. 2 and 5 are not powers of the same number here. So I must use logarithms here. So let's first write that little comment down here, that 2 and 5, which are the bases here, are not powers of the same number. And because they're not powers of the same number, I cannot use rules of exponents here. I'm going to have to use logarithms. So must use logarithms here. And so what you're doing here, just like we had a property up above, you're using a property of logarithms to solve this type of equation. The property of logarithms you're using is this, that if you have two numbers that are equal, if capital A is equal to capital B, then it has to be true that the logarithm of both sides, no matter what the base is, if you use the same base on both sides, that their logarithms have to be the same also. Logarithm base B of A has got to be equal to logarithm base B of B. little b of capital B there. So what that actually implies here is, the way most students say this in words, is they say, well, what I'm going to do then is I'm going to take the logarithm of both sides of the equation. And it doesn't matter what base, but because you're going to use a calculator at the end of a problem like this, you either use base 10 or base e. Either use a common logarithm or a natural logarithm to do this, because you're going to use a calculator at the end on this problem, this kind of problem, to get a decimal approximation for the solution. So if I use base 10 logarithm, then I'm taking the log of both sides of the equation. Make sure you take the log of both sides. So you have log of 2 to the x, right? This is 2 to the x over here, and it's log base 10, remember, because this is a common logarithm, equals log of 5. I'm just taking the common log of both sides of the equation. Now, the reason why this will work, why this will allow you to solve the equation, is because I have got the power rule for logarithms right here. That was the other big thing we talked about last time in lecture, were the properties of logarithms. And I can use the power rule of logs on the left side of this equation, and I can actually bring the x down in front as a factor. And so you have x times log of 2, just bringing that, remember, you can bring that exponent down in front as a factor, equals log of 5, like that. And then you can solve for x. Solve for x by just dividing both sides by log of 2, because log of 2 is a constant, so you end up with log of 5 divided by log of 2, like that. And that is the exact value of the solution. Now, on a calculator, what you do is you just enter it, on a graphing calculator, you'd enter it log of 5 divided by log of 2. Just make sure you enclose both the 5 and 2 inside parentheses there when you do that. So I'm entering that in my calculator right now. And when I get that, when I enter that, I end up with approximately 2.322. I'm going to round these to 3 decimal places. So approximately, that's why I'm using a squiggly equal sign there, 2.322. And, what are you saying here? That 2 to the 2.322 is equal to 5 approximately. And that 2.322 makes sense because, if 2 squared is equal to 4, which is too small, right? 4 is smaller than 5. And 2 to the 3rd power is 8, which is too big. So it makes sense that we have a number between 2 and 3. It would give us 5, and which is exactly what we got right here, 2.322. And so that would be the solution I'll be looking for. On your exam, I will say round these solutions to the nearest 3 decimal places. Round it to 3 decimal places, something like that. All right, so that outlines how we're going to solve these kinds of problems. That's the method that we're going to use to do this. Now, I'm going to look at a little bit more complex problems in slightly different situations as we go through this, but that outlines pretty much what we're going to be doing. So that's good in that we've already got the mathematics here that we need to solve this kind of problem. So the next one, let's say we have 5 to the 3x plus 1 is equal to 10. Now, once again, 5 and 10 are not powers of the same number, so I must use logarithms here. 10 is not a power of 5, remember. It's 2 times 5, but it's not 5 to a power. And so I can't use rules of exponents here. I have to use rules of logarithms. So I take the log of both sides of the equation here, right? 5 and 10 are not powers of the same number, so must use logs here. So in this problem, I think what I'll do is, last time I used the common logarithm. On this one, I'll use the natural logarithm just to show you that it doesn't matter which one you use. So I take the natural log of the left side equals the natural log of the right side, like that. All right, and so when you do that, you've got the power rule on the left side. So I can bring that 3x plus 1 down in front of the logarithm. Now, I do want to point out that what I've just written, what I've just written is incorrect. And this is a common mistake here that you've got to be careful about. That's incorrect. Because I don't have parentheses around the 3x plus 1. When you bring an exponent down in front that's got terms in it like that, addition or subtraction, you have to use parentheses around that exponent there. And so this is the correct version right here. So be really careful about that. You can make an easy mistake there if you're not careful. All right, and now you solve for x. So now solve for x. And to solve for x here, you know, what I might do, there's a couple ways you could do this, but I might go ahead and divide by natural log of 5. So this is natural log of 10 divided by natural log of 5 right here. And then you literally subtract 1 and divide by 3. So you have natural log of 10 divided by the natural log of 5 minus 1, like that. And then you're going to divide that entire number by 3. Now it looks like a nasty form. There's nothing wrong with this form inherently. You're dividing the whole thing by 3 like that. And actually on a calculator, that is not that bad to enter that. And so I had no problem with you writing it this way. Now, just to show you, sometimes you'll see, like in a lab, if you go to a lab to get help, you may have somebody tell you to do the problem this way. And there's nothing wrong with this either, but it looks different. You may have somebody tell you, hey, you've got to multiply through using the distributive property here, which would give you 3x natural log of 5 plus 1 times natural log of 5, which is just natural log 5, equals natural log of 10, like that. And then you solve for x on that one, and so if this is going to look different, you're going to have 3x natural log of 5 equals natural log of 10 minus natural log of 5. Right, you just subtract natural log of 5 from both sides there. And then you finally divide by 3 natural log of 5 on both sides of the equation. And so you end up with x to be natural log of 10 minus natural log of 5 divided by 3 natural log of 5. Now that answer doesn't look like our answer at all, but they are exactly the same answer. These are equivalent right here. I usually find that most students, the first way I did this is probably they work through it a little bit easier, a little bit better, and then they end up with the correct answer there. The other way, I see some mistakes sometimes. But I have no preference there at all. You have to be careful about the way WebAssign wants you to write things out also. Now on a calculator, to show on the calculator how you're going to enter my answer right here, you need to be really careful in that the entire numerator needs to be put in parentheses because there's a subtraction there, and I get students sometimes will forget to put parentheses around the entire numerator. So you really need to be careful with that. And then so you enter natural log 10 divided by natural log 5 minus 1. Calculator is going to, your calculator is going to obey order of operations there, and so it's going to do the division first and then subtract 1, which is what you want. And then you can take all of that and divide, so you enter divided by, and then it's going to divide by 3 like that. All right, and so when I do that, when I put the entire numerator inside parentheses, so you get natural log 5, natural log 10 divided by natural log 5, and then subtract 1, close off those parentheses, and then divide by 3, and I get 0.14355 as my answer. So approximately 0.144 to 3 decimal places, 0.144. And remember, you can always check your answer here. I frequently, well, most of the time, students don't do that, but it's not a bad idea that you can take that 0.144 and you take your original equation and you actually check it. And so if you're checking x equals 0.144 there, Right, there's my equation, and then I put 0.144 in place of x, like that. And it's a little messy, but you have a calculator, so you can use that to your advantage here. So let's see, times 3 plus 1. And so this becomes 5 to the 1.431 power equals 10. And I'm still trying to check this. And then I take 5 and I raise it to that power. So I'm kind of doing this in several steps. And I get 10.005. Right, and so that checks because I rounded the decimal up there, and so that certainly tells you that you're correct here, that you're likely got the right answer, the right solution here. So 0.144 is the solution that we're looking for this equation. All right, the other thing I want to point out in this problem, before I leave this, so I've done this problem multiple ways now, but one other thing is because the right side of the equation was 10, you might actually, instead of using the natural log like I did, you might use just log base 10, and I'll show you why that ends up maybe making your life slightly easier on a problem like this, is if you use log base 10. So the left side, you're not really doing anything different. You have 3x plus 1 that you bring down as a factor. But this is where this makes things maybe a little bit nicer, is that log of 10, that's log base 10 of 10, remember, that's equal to 1. And so it does simplify a little bit. Now that may or may not help you in a problem like this, but sometimes if you see a base of 5, using the log base 10 makes your life a little bit easier, possibly. And then you just solve for x. You divide by log of 5, and it may not make your life any easier here. I don't know, but this is what you'd end up with. You'd end up with x to be 1 over log of 5 minus 1, all divided by 3. It doesn't make things a lot simpler here, but in some contexts it might make your life easier. You're still going to end up with the same solution, certainly at the end here, 0.144. So that still gives you another way to look at this particular problem. All right, so let's continue on with this exponential equations part 2 here. So let's say we have an equation that looks like this one. Now this is actually problem number 20 on page 535 of your book. This is section 6.6. This is problem number 20. And you have 2 to the x plus 1 equals 5 to the 2x minus 1. Now notice there's x's in the exponents on both of those, both sides of the equation. So you take the log of both sides. So you have log of 2 to the x plus 1 equals log of 5 to the 2x minus 1. It doesn't matter what base you use here. For the logarithm. So bring the x plus 1 down as a factor using the power rule. Bring the 2x minus 1 down in front using the power rule. Notice I had to put parentheses around both of those. See, and to solve here for x, really your only option at this point is you have to use the distributive property. Because there's x's on both sides, you really have no choice. And so this gets kind of messy here at the end. I'm going to be very honest with you. This is going to get to be kind of yucky. So use the distributive property there and multiply through by log of 2. Use the distributive property here and you multiply through by log of 5. So that would give me x log of 2 plus 1 times log of 2. Right, you're just multiplying through by log of 2 equals 2x times log of 5 minus 1 times log of 5. Like that. And that's all multiplication in the front like that. All right, so you've got the exponents all eliminated from the problem. And so now you have to look at where the x terms are. So notice that this is an x term right here. and this is an x term right here. And so those terms need to be on the same side of the equation. You can't have them on different sides of the equation if you're going to solve for x. So I might subtract 2x log of 5 from both sides. So I subtract 2x log of 5. And so that's going to move all the x's to the left side of the equation because I'm subtracting like that. So I've got x log of 2 minus 2x log of 5 on the left side of the equation. And then the constant terms you would want on the other side of the equation. So this log of 2 that I've got right here, I'm going to want to subtract that one from both sides. And so I'll subtract log of 2 to move it to the right side of the equation. And I'll subtract log of 2 over here also. And so that gives me the right side of the equation to be negative log of 5 minus log of 2, like that. So I have all the x terms on the left side, all the non-x terms on the right side of the equation. Now what you do to solve this is you factor out an x. Factor out x on the left side of the equation, right? Because you're trying to solve for x, so you factor it out. So you have x log of 2 minus 2 log of 5 on that side of the equation. On the right side, this is kind of yucky, and what you might want to do is try to combine these two terms. And let me show you what you can do here. Notice that both of them are negative here, so if they're both negative, factor out a negative 1. And so that gives you just positive log of 5 plus log of 2. Like that. And now you can actually simplify inside both of those brackets. Notice what we can do here. Inside both of the brackets, so let's see, simplify using log rules inside each bracket. And that's what I'm going to do in this step right here. So this is what I'm talking about. On the first bracket, you're contracting. Remember how we talked about contracting logarithms last time, right? Where you're putting them all together. So I could bring that 2 up as an exponent. So this is a log of 5 squared right here. On the right side, log of 5 plus log of 2, I could combine, there's no exponents there, so I can combine those two using the product rule because it's an addition problem. So this is log of 5 times 2. Like that. And let me erase that and just put that inside parentheses since I have brackets around the outside. So this is log of 5 times 2, like that. That's just the product rule. So then on the left side, continuing on with simplifying here, this is be log of, and this is going to be quotient rule because it's a subtraction problem, right? And that's the quotient rule for logarithms. So this would be the log of 2 divided by 5 squared, which is 25. So log of 2/25. On the right side of the equation, I have the negative of log of 10. And this turns out nice because log of 10 ends up being 1. And so you have x log of, this is a yucky problem as you go back and look at it, isn't it? Log of 2/25 equals just negative 1 because log base 10 of 10 is 1. And finally, you solve for x. And you solve for x, you get negative 1 divided by log of 2/25. Like that. And so this is really, really kind of a yucky problem. Now, you can work through things slightly differently as you go through there. And you could have gotten that answer, you know, in a slightly different form also. This would be just fine right here. Now, on a calculator, the way you'd enter this is you'd put -1 and then divided by and then log, and the fraction shouldn't bother you. This is just 2/25 that you put inside parentheses. So that's how you'd enter this on a calculator. So you have -1, -1 divided by, excuse me, log of 2/25. This problem's got me so choked up because it was so long here. And I think I've got that entered correctly. And now it tells me I had a syntax error, so I have to go back and look and see what I've entered. Oh, yeah, okay. And so I'm getting approximately, and you should probably stop the video at this point one way or another and see whether you can get the same answer, but I'm getting 0.912 approximately to 3 decimal places is my solution. And so you should definitely go in there and stop the video here if you're watching this recorded and see if you can get 0.912 as the solution here. And as always, what can you always do at the beginning is you can check your work and see if 0.912 looks like it would be the solution to this equation. Remember, this is a rounded decimal, and so it's not going to be exact, but it should give you a pretty good idea that you're right. So if I check here, I take 2 and I put 0.912 in there, and I get 2 to the 1.912 power. And so that value on a calculator, 2 to the 1.912 power, is about 3.763. 3.763, like that. And then on the other side, you get 5 to the 2 times 0.912 minus 1. So let's see, 2 times 0.912 is 1.824 minus 1 is 0.824. And so I get 5 to the 0.824 power, and I'm keeping my fingers crossed here. So when I raise 5 to the 0.824 power, I get 3.766. So, and that gives me a really good idea. To 2 decimal places, those numbers agree that because of rounding error, that should be fine. So there, 0.912 is my approximate solution here. Now the good news here, this is absolutely the worst it's going to get. And in fact, you may see a WebAssign question like this, but I probably won't give a problem that's this bad. In fact, I said I probably won't. I won't give you a problem this bad for this kind of exponential equation on the exam, just so you know. So hopefully that makes you feel a little bit better, because that's a pretty gross problem. Definitely. All right, let's look at the next problem here. Let's say we have e to the x plus 3 equals 20. E to the x plus 3 equals 20. Now, also an exponential equation, the base here is e. When you have a base of e like this, always use ln on both sides here. That's the logarithm you want to use, because you want to make your life as easy as you can. That's what you need to do here, and I'll show you why that's true as we go through this. So this is the natural log of e to the x plus 3 equals the natural log of 20, right? Use the natural log on both sides. And then you bring the power down in front. So you have x plus 3 times natural log of e equals the natural log of 20. And this is why this, using natural log, is what you need to do in a problem like this. Remember that the natural log of e, that's the power you raise e to get e. The natural log of e is always equal to 1. See, so that really does help a lot in this context, because this natural log goes to 1. And you're just left with x plus 3 equals natural log of 20. That's very helpful. And then just subtract 3 from both sides, and you have solved for x. X is the natural log of 20 minus 3. And so that problem works out pretty darn smoothly. You want to take the natural log of 20 and then subtract 3 from that. So let's see, so the natural log of 20 minus 3. Make sure that you close off the parentheses on the 20 when you enter this. And I get approximately, to 3 decimal places, negative 0.004. And so that is my solution to this equation. So this is what we call the exact solution right here. I haven't really mentioned that, but that's the exact solution. This is the approximate solution using a calculator. I will be asking you for the approximate solution, and I'll say round this to 3 decimal places, quite likely. So, all right, the next example here. So that one worked out pretty well. Let's say we have e to the 4x minus 3 power minus 30 equals 70. All right, we'll look at that equation there. Now, to solve for x here, if you're going to take the log of both sides, you have to have that exponential expression by itself. So what you need to do is you need to isolate the exponential expression before you do anything. A common mistake I see students make. But isolate the exponential expression first. So you need to do that. So when I say that, in this case, what that means is just add 30 to both sides. So you have e to the 4x minus 3 equals 100. And see, now the exponential expression is isolated. It's by itself. Now you take the log of both sides of the equation. And remember, use natural log because this is base is e here. So this is the natural log of e to the 4x minus 3 equals the natural log of 100. Excuse me, sorry. And then use the power rule. Remember, this is the power rule in this step right here. And this is why you're using logarithms is because you have the power rule. So you have 4x minus 3 you bring down as a factor times the natural log of e equals the natural log of 100. Remember that the natural log of e is equal to 1. So this factor goes away, which is good. So you have 4x minus 3 equals the natural log of 100. And then solve for x. Right, so I add 3 to both sides. I'll put the 3 in front. It doesn't really matter if you put it in the front or in the back. And then divide by 4. So you have 3 plus natural log of 100, all divided by 4. On your calculator, please remember to use parentheses here. So on your calculator, you have to put parentheses around that numerator. And so notice you end up with 2 sets of parentheses in here because you have a set of parentheses around the 100 and a set of parentheses around the entire numerator, and then divided by 4. So really be careful about how you enter that on a calculator. All right, so I put 3 plus the natural log of 100. Close both sets of those parentheses, and then divide all that by 4, and I get 1.901 approximately is the solution, 1.901. And that is the approximate solution here for this equation. Okay, so that's not too bad. And so let's see, let's finish this type of problem here. This is on again on section 6.6. This is problem number 28 out of your book. You have 3e to the 3 minus 3x plus 6 equals negative 31. Like that. And I tell you what, I'm going to actually change this problem. I don't like it with a negative 31 there, so I'm going to put positive 31. All right, and because I want, they actually set it up so that there wasn't a solution, but I prefer there to be a solution to the equation. So, All right, so to solve this, again, like I said in the last problem, isolate the exponential expression. You've got to do that first before you try to use logarithms. Don't use logarithms in this step. Isolate the exponential expression first. That's important. So in this problem, that actually takes 2 steps because you have to subtract 6 first. So you get 3 times e to the 3 minus 3x equals 25. And then you do have to divide by 3 because the exponential expression was still not isolated. So you have 25 divided by 3 over here. And now you can take the log of both sides. So use ln on both sides. Right here, you're isolating the exponential expression. And those steps, now you're using ln on both sides. So you have the natural log of e to the 3 minus 3x equals the natural log of 25/3. And then use the power rule, like we've been doing in all these problems. Don't forget the parentheses. So this is 3 minus 3x in parentheses times the natural log of e equals the natural log of 25/3. Don't forget that the natural log of e is equal to 1. That's occurred now a couple of times on problems. So this factor goes away, which is great. So you have 3 minus 3x is equal to natural log of 25/3. And then subtract 3. We're getting close here. So the natural log of 25/3 minus 3, or you could put negative 3 at the beginning. And then finally divide by negative 3. It's not too bad. The steps are pretty well similar to what we've done in the past here. Just a little bit of tedious work at the end in this problem. So on your calculator, try to emphasize how you're entering things on your calculator. So put parentheses around the entire numerator. Make sure you do that. You also need parentheses around these 25/3. Not a bad idea to actually write out how you're going to enter this on a calculator before you actually enter it. Also remember that this negative sign right here, this is not subtraction, that's a negative sign. And so on your calculator, that's right underneath the 3 key is the negative sign, or just to the left of the enter key, right? That's the negative sign. And I get students all the time using the wrong symbol on their graphing calculator. Just to kind of, if you get a graphing calculator in front of you, the keys at the bottom look like this. And I want to make sure that you use the right symbol here. And so these are the keys at the very bottom of your calculator. And so notice that this key right here, if you get a graph or TI-83 or 84 out, this is a negative sign, or I'm sorry, this is subtraction right here. That's that key right there, that button. And this is the negative sign down here. And I get students all the time using the wrong symbol there. So make sure that you use the correct symbol when you're doing this on a calculator. All right, so on my calculator, let me enter this then. I have the natural log of 25 divided by 3, close off the parentheses there, minus 3, close off the entire parentheses out of the numerator, and then divide by negative 3. And I get my answer to be 0.293 here for x. So x is approximately 0.293. And again, certainly you could check this solution to make sure it actually works out in this equation. All right, so now as an application for these kinds of problems. We were looking at compound interest problems a while back, and this kind of equation comes up with compound interest problems. So let's say that I invest $1,000 in an account that pays, let's say, 3% compounded continuously. So remember, compounding continuously means this is the compound interest formula I'm using, A equals PE to the RT. Don't forget that I will supply you that formula on a test if you need it. And the question is, how long before the money doubles? Right, how long before it doubles? So when you're talking about doubling like that, first of all, and how long obviously means that t is our unknown in the problem. The principal is $1,000. The interest rate is 0.03 because it's 3%. And A, because we're talking about doubling, is going to be $2,000, right? Because we started with 1,000, it's going to double to 2,000. And so you end up with this equation, 2,000 equals 1,000 e to the 0.03 t. And notice you end up with an equation similar, very similar to what we've just been talking about. It's an exponential equation where I can use logarithms. I first isolate the exponential expression. I divide both sides by 1,000. And so that gives me 2 equals e to the 0.03 t. And just like I've been doing on the last couple of screens, I take the natural log of both sides of the equation to solve this. Like that. And then I use the power rule, bring the 0.03t down in front, and that gives me just the natural log of e. We know that that's 1 right there, and so you get natural log of 2 equals 0.03t. And then finally you divide by 0.03, you get natural log of 2 divided by 0.03 is equal to t. And so that would be our solution. That's the exact value. So then I take the natural log of 2, I divide that by 0.03, and I get 23.1 approximately. T is equal to 23.1. And so that would be 23.1 years before the money doubles in an account like that. So it would be it's a long time before it doubles. All right, so every 23.1 years, this money is going to double in this particular problem. So in the next 23.1 years, notice that if you started with 1,000, then what do you have? You have 23.1 years, the money doubles, and now you have 2,000. In the next 23.1 years, the money doubles again, but now it's 4,000, right? Because so it increases by 2,000 there. In the next 23.1 years, the money doubles again, and so now it's 8,000. So notice that even though it's doubling each 23.1 years, the amount that it's going up is certainly getting bigger and bigger each time. That's the idea for compounding, right? And so on, right? It keeps on going like that. All right. So that's our discussion of exponential equations. And so what I'm going to do here now is finish with talking about logarithm equations. So we're going to move on to log equations. And basically the way, now the textbook does not do this, but I kind of separate them out purposely so that we just have some way to identify the equations. And I break these up, log equations, up into two groups. One are what I call type 1 log equations, and these are equations where you have logarithm base b of some expression equals a constant. And then type 2 log equations where you have logarithm base b of some expression equals logarithm base b of some other expression, like that, where you have a logarithm equals a logarithm. And so we're gonna first deal with the type 1 log equations here, and then if we have time, we'll start talking about type 2 log equations. Now, type 1 log equations, notice I put base b logarithms there. It doesn't matter what base logarithm you've got. So notice that, if you've got a simple equation like this, let's say logarithm base 3 of x is equal to 4, like that, right? That's an example of a type 1 logarithm equation. Logarithm of some expression equals a constant. And all you've got to do, right, is you just, in the method here, is just to write an exponential form. Right? That's how you solve the equation. It's actually a pretty simple solution, or solution method here. So the exponential expression, or the exponential form for log base 3 of x equals 4 is simply 3 to the 4th is equal to x, or x equals 3 to the 4th, either way you write it. So that's the exponential form right there. Right? And then, just multiply that out and you're done. You get x equals 81. And that's your solution to that equation. Right? And again, what you're doing is you're writing in exponential form here. We haven't done that in a few days, but we certainly have practiced that a lot in lecture. There's no question about that. Okay, so that seemed to be pretty straightforward. Logarithm base 2 of x plus 4 equals negative 1, let's say. So exactly the same method here, right? You're writing an exponential form. That's the key at the beginning. Once you've got logarithm equals a constant, just write the equation in exponential form. So this would be 2 to the negative 1 equals x plus 4. Right? And then 2 to the negative 1, don't remember, that's not negative 2. Remember, the negative exponent turns that into a fraction, right? It flips the 2, makes it 1/2, or 1 over 2 to the positive 1 equals x plus 4. And then just subtract 4, right? So you have 1/2 minus 4 equals x. That's 1/2 minus 8/2 equals x, or negative 7/2. Negative 7/2 equals x. And there's your solutions. Okay, so not too bad. Let's say we have log of 2x plus 1 equals 2. Log of 2x plus 1 equals 2. Now don't forget that when you've got a base, no base written, that this is a common logarithm. Don't forget that this is understood to be base 10 right here. So in exponential form, this would be 10 raised to the second power equals 2x plus 1. Right? It's 10 to the second power because the base on the logarithm is base 10. And then just solve. You get 100 equals 2x plus 1. Solve for x, you subtract 1, you get 99 equals 2x. And then divide by 2, and you get 99/2 equals x. And so 99/2 would be your solution, or 44.5 if you wanted to write it as a decimal. Okay, that's not bad at all. Another example, let's say we have natural log of x plus 2 equals 3. Natural log of x plus 2 equals 3. So don't forget that with the natural log that this is a base e logarithm. So when you write in exponential form, you end up with e to the third power equals x plus 2. right? Because the base on that logarithm is a base e. So you have e raised to the third power. Remember, the logarithm is always equal to the exponent. And then subtract 2, and you get e cubed minus 2 is equal to x. Now in a calculator, don't forget that e cubed is, let's see, e cubed, you enter that as second ln 3, right? And so when you enter e cubed minus 2, first of all, e cubed is about 20.085. So you have 20.0855, etc., minus 2 equals x. So x would be approximately 18.086 if you're going to round this to 3 decimal places. 18.086. Sometimes you're going to have to round these at the end, especially when you've got dealing with base e logarithms like this. All right, so let's see if we've got, so that hopefully is working out okay. Let's go on to another example here. Let's say we have something like this. Let's say we have, and this is problem number 34 on in your textbook on that section 6.6. You have 2 log of 8n plus 4. So don't forget that log means base 10 logarithm, plus 6 equals 10. So on this one, what you need to do is you need to isolate, certainly you need to isolate the radical, or I'm sorry, not isolate the radical, isolate the logarithm before you do anything. So isolate log, get the logarithm by itself. So in this problem, I'm going to subtract 6. So you have 2 log of 8n plus 4 equals 4. And then divide by 2. So you have log of 8n plus 4 equals 2. And so that's, these steps right here are isolating the logarithm, right? You're trying to get the log by itself. And then don't forget that this is a base 10 logarithm. Tried to really emphasize that over and over again. And you're going to write in exponential form. So in exponential form, this would be 10 to the second power equals 8n plus 4. And so that's our exponential form right there. All right, and then just solve for n at the end. So you have 100 equals 8n plus 4. Subtract 4, you get 96 equals 8n. And then divide by 8, and that actually goes in evenly, right? It divides to give you 12, so m is 12 in this case. And that would be our solution to this equation. All right? So, and again, don't forget you can check this. You know, don't ever forget that you can check these. And so, and sometimes, by the way, and we're going to talk about this more on Monday when we come back, is that you for our next lecture, is that sometimes you really have to check here. So I'm putting 12 in for n, right? And so I notice I put 12 in on the left side of the equation. So that gives me 2 log of 96 plus 4 plus 6. So that's 2 log of 100 plus 6. And log of 100, that's the power you raise 10 to get 100. That's equal to 2. So this is 2 times 2 plus 6. Let me emphasize here that log of 100 and 2 are the same thing, right? Because that's the power you raise 10 to get 100. And that's 4 plus 6, or 10. And that's, sure enough, that's what I have on the other side of the equation. And so that would check. Never a bad idea to check the solutions like that. All right, the next problem. This is just an example we're going to work here. Let's say we have log of x squared minus 10 plus log of 9 equals 1, like that. All right, so when you have an equation like this, I've got 2 logarithms in here. So notice what I'm going to have to do is I have to combine these, and I combine using the product rule. Because you're trying to get a logarithm by itself, so you have to take the 2 logarithms and combine them. And in this case, it's the product rule because it's addition. So this is the log of 9 times x squared minus 10, like that, equals 1, or x squared minus 10 times 9, either way you want to write it. So this is log of 9x squared minus 90, like that, equals 1. And now write in exponential form, right? This is a base 10 logarithm, so you have 10 to the first power equals 9x squared minus 90. And so you get, let's see, you get 100, because you're getting the solving for x now, so I'm just going to add 90 to both sides. So I'm just adding 90 to both sides right here. And so you get 100 equals 9x squared. And then divide by 9, and so you have 100 over 9 equals x squared. And then you can use the square root method here, and you actually get a plus or minus 10/3 equals x. And so those are going to be the solutions to this equation, positive 10/3 and negative 10/3. All right, and so let's see, I think it would probably not be a bad idea to work one more problem that's a type 1 logarithm equation, and then that will be it for log equations. So let's say we have a problem that looks like this one. Okay, so let's see. Let's say we've got logarithm base 2 of 2 plus logarithm base 2 of 3x minus 5 equals 3. So again, I would combine these using the product rule. And so this would be logarithm base 2 of 2 times 3x minus 5 equals 3. Or just logarithm base 2 of 6x minus 10 equals 3. Just multiply that out inside the brackets there. And then you will write in exponential form. So in exponential form, this would be 2 to the third power equals 6x minus 10. Right? Remember, the logarithm is equal to the exponent, so the 3 has got to be the exponent. The base on the logarithm and the base on the exponential expression have to be the same. So this is 8 equals 6x minus 10. Add 10 and you get 18 equals 6x. And finally you divide by 6 and you get that x is 3. All right, so that's not too bad right there. And then finally, the last problem we're going to look at. Let's say we have log of 2x plus 1 minus the log of x equals 1, like that. So in this problem, right, if we want logarithm equals a constant, remember in all these type 1 equations, I haven't been writing this down much, but on these type 1 equations, you want logarithm equals a constant. Okay, so I have to combine these logarithms. And in this case, because it's subtraction, I combine those using the quotient rule. And so this is log of 2x plus 1 over x, like that, equals 1. And then this is a base 10 logarithm, right? So when we write in exponential form, this would be 10 to the first equals 2x plus 1 over x. Right, remember, the logarithm is equal to the exponent, so, and the base on the logarithm is 10. Base is 10 here, and it's got to be equal to the exponent. The logarithm is equal to the exponent, so 1 has to be the exponent. That's why you get 10 to the first. Solve this equation by getting rid of the fraction, multiply both sides by x, so you get 10x equals 2x plus 1. Subtract 2x and you get 8x equals 1. Divide by 8, you get x is 1/8. And there's our solution to this equation, x equals 1/8. All right, and so there we go. There's our examples for type 1 logarithm equations. So next week, on Monday, we will look at type 2 log equations. And then on Wednesday, no lecture because I will be on campus that day for help. And then on Thursday, I'll be on campus again on that day. And exam 3 window opens. Exam 3 opens that day. So that's next week, okay? So remember, you do have WebAssign homework due this Sunday, so keep that in mind also. So I hope everyone has a great week. Please don't hesitate to stop by for help. In my WebEx office or on campus, I will be more than happy to help. Remember, I also will sometimes make office hours by appointment. So online office hours. If you can't make my regular hours, try to make some kind of an appointment. So try to make an appointment. If you cannot come by during regular hours. Have a great day.